Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Try this. Place your left hand on top of your right. No matter how you move your fingers around, you can't superimpose one on top of the other. Your hands have a geometric property known as chirality, or the absence of mirror symmetry. Nature is full of chiral structures, says Irmgard Bischofberger, a physicist at the Massachusetts Institute of Technology. For example, the placement of organs in mammals lacks mirror symmetry. Famously, there's also the right-handed double helix structure of DNA. Behind the existence of left-handed and right-handed structures lies a fundamental question. How does nature create objects with this asymmetry?
It's still a mystery of how chirality emerges in nature.
Bischofberger and her team have recently conducted an experiment with liquid crystals that could bring insight. Liquid crystals are a distinct state of matter that can flow like a liquid, but the molecules are oriented in a particular direction, like a solid. They used liquid crystal molecules called disodium chromoglycate. In their experiment, the liquid crystal molecules are dissolved in water. The molecules are little disks that attach to each other to form linear rods. These rods initially arrange themselves in parallel, but when Bischofberger forces the molecules through a thin channel between two glass plates, the rods twist with respect to each other.
They start to assemble in kind of spiral structures where each molecule with respect to the next one is slightly rotated, such that globally they form a twist-like structure.
This basically transforms the linear molecular structures which have mirror symmetry into spiral structures without mirror symmetry. They made a chiral structure out of a non-chiral one. They observed these structures by imaging them using microscopy.
Beyond a certain critical flow rate, this nicely aligned material starts to all of a sudden first become kind of randomly oriented, but then starts to assemble spontaneously into these large-scale stripe-like patterns. So they look a little bit like a tiger under your microscope.
Their results are unusual because typically in nature, large chiral structures either form in two ways. In the first way, they're composed of smaller chiral components. The nucleotides that make DNA, for example, are chiral. Or you get chirality by performing some sort of twisting motion, such as when you twist two strands of hair together. Neither is the case here.
What's exciting in the example here is that our material is composed of non-chiral building blocks, and we don't have any chiral input, and yet the material spontaneously breaks mirror symmetry. And so it seems to suggest kind of a different way to forming chiral large-scale structures.
She says it's also noteworthy that their method creates chirality so simply. The molecules spontaneously become chiral by flowing through the channel. Her team is now changing other properties of the system, such as changing the patterns they scratch onto the surface of the glass that the liquid flows through. They're studying how that affects the structure of the liquid crystals.
What we start to see in our experiments is that then you get other types of flow-induced structures in the material.
She also says that chiral liquid crystals could have technological applications. For example, when light hits the twisted rods that make up the liquid crystals, the structures delay the travel of the light based on wavelength. Researchers could exploit this behavior to create an optical sensor. This work was published in a recent issue of Nature Communications. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.